Closing in on the end of this chapter, and we are taking a look, just scratching the surface of the kinetic molecular theory of gases. Now, when some of you brave souls decide to take physical chemistry independent study with me, we will do this in depth. So, to understand gases, the basic setup, and I hate how textbooks use, like chemistry textbooks use U for this, because that usually means energy, but in this case, I just use the same notation as the textbook, but it's a velocity, okay? It's, you basically model your gas inside of a box, sides A, B, C, then you have an area A that you're going to be examining inside that box. Now, we're really only looking at a singular component of velocity, because you'll be happy we're not doing this. Gas molecules, do they only travel that way? And they can go just all over the place. So like when you start to get more advanced, you start modeling this as where you're going to have some arbitrary direction. And you'll have your velocity will be a vector. So of course, then you would have, well, let's say, I'm going to do this first. I'm going to go to there, to there, and straight over. And so when you study this, you know that these are so you're going to have UZ. You're also going to have, well, I'm going back like that. No. So these are all unit vectors where you have UY, UX. You're only looking at a single dimension of this possible vector space. It's enough to get the point across. By the time you take physics with me, we'll do two of these dimensions. Except today, because people complain, we actually did a surface integral over a spherical space. But you know, that's just for fun. So your molecule is going through, what we're trying to get to inevitably is the ideal gas law. So your molecule goes through the box, it hits your surface area A. So A is, of course, B times C. And so what happens when, you can think of it, like if you throw a ball against a wall, what happens? Bounces back at you. So what happens is you're getting what's called a change in momentum. So your first momentum for, ignore the axes, this is for the box. That's the positive x direction. We need that in vectors. So your first momentum is going that way. Then it bounces. And you have your reverse momentum. So one of them will be going a positive direction, the other one will be going a negative direction. So we say that our initial momentum is the mass of the molecule, the initial velocity in the x direction, your final momentum we can just go ahead and call that U1x because we have the negative sign to denote the final. Again, you see initially it's going in the positive direction, it bounces, and now it's going in the negative direction. So your difference in your momentum well, let's make this easier. So P final minus P initial. Minus negative. No, fine. We'll do it the other way around. It's going to be a magnitude. Again, in physics, negative or positive indicates a direction. Okay. What we end up getting is a magnitude of this difference in our momentum. Because we're not really worried about the direction it's going. We want to know how big it is. And so a magnitude, does anyone know how to write that mathematically? Magnitude. Absolute value. So when we're looking for a magnitude, you're not going to get a negative sign. It's how big is it? Because again, if you think of the number line, I could go to a -5. The magnitude of that is still 5. Now, we're going to work with this. Has anyone ever seen this? That is Newton's second law. So we know delta P, so that's going to be 2 mass times velocity, delta T. Has anyone ever heard an area of science study called dynamics? So what do you think the difference between dynamics and statics is? Nope. This equation here is a dynamic equation. So if you're ever looking at dynamics versus statics, statics is a single instance. Dynamics is evolution over time. So your dynamic systems, you're observing and modeling how they change over a given period of time, whereas statics is, well, what's the system like right now? Okay. Now, Newton, oh, look, I already put it in there. Whoops. Okay, Newton also gave us, when you take physics, these are going to be your best friends, this set of equations called kinematics. And we're going to be looking at one that's delta x. So the change in your distance is going to be 1/2. Well, we'll just keep using the u. Initial velocity plus final velocity, delta t. Now, so here's something to realize. The ball hits the wall, it bounces back. Initially, the velocity is that way. So in order for the ball to do a complete turnaround and come back, at some point its velocity against the wall has to be what? 0. So we're going to use that as our situation we're looking at. That velocity is going to go to 0. Which means that now we're going to have delta x equals 1/2 initial velocity, delta t, not always. It's just it's a way we can model this system without bringing in a bunch of extra steps. Now, we've actually come across something here The kinematic actually ended up giving us, we know from other kinematics that the acceleration of this ball oh, no, hang on. I wrote these so long ago and I'm on 4 hours of sleep. Give me a second. Oh, yeah, not acceleration. A was 1/2 UIX delta T, because I said the wrong thing. I'll show you what I mean. A, delta X. So now we have a definition for that side of the box. We are going to go back to Newton's second law, force, delta P over delta T. So we know that the delta P is 2 times the mass times the velocity over, now we have, if we solve this for delta T, we're going to get 2 times the side A of the box that the gas is in, U1X. Tell me what I did here. So this is going to become 2 velocity squared over 2A. What did I do there? I go from here to here. What I do? Well, so yeah, I have a fraction in the denominator. So when you have a fraction inside a fraction, the denominator in that denominator then flips up. It's like flipping it upside down and multiplying. So that means our force is going to be mass times velocity squared over the length of the side of that box A. We're going to use this because what do we know about, so let's get a definition of pressure. Real basic one. Pressure is what over what? Force per what? So the square inches is a what? Thank you. Area. Force per unit area. Okay. Now we know that our force in our area was B times C. This is going to give us mass times velocity squared over A, B, C, which, think about the box. What does A times B times C equal? Say volume. So now we have mass times velocity squared over volume. So now imagine this box has multiple molecules in it, all existing to create a similar pressure. How do we account for all of them? How do we account for the total pressure in the box? This gave us the pressure of a single molecule. So yeah, and what do we do with those? Add them together. So the total pressure in this box will be the sum of the pressures of each individual molecule. And so this all the molecules are identical, so we're going to leave mass the same. What can change is the velocity of each molecule. So we're essentially adding together all those velocities so we can pull out. When you have a sum, you can pull, just like an integral, you can pull constants out to the front. So all of those velocities, okay? Now, what we've done here is we're very, very close to, in statistical mechanics, what we call an average value. Okay, so if we wanted an average velocity for all the particles in this box, I'll show you the notation. You don't have to remember it, but this is how you do it in statistical mechanics. We start using what's called Dirac notation. Average value of the square velocity, 1 over n, and our sum of all of those velocities. N, what do you think that equals? Nope. Nope, that's little n. Think of molecules in the box. Big N is the, do you see what? Yeah, number of molecules in the box. So another way you might see this written, so we use the bracket notation in statistical mechanics. You might see someone do like that, your average value. Now, we have this value, we have this for our average value right there. We have this for our total pressure. We're going to use a physics trick called multiplying by 1. So if I multiply by 1, I only have to, whatever I do, I only have to do it to one side of the equation, because otherwise I'm still multiplying the other side by 1. It doesn't change. Except we multiply by 1 in a way that helps us. So our total pressure, we're going to have our mass over velocity, and then we're going to have number of molecules over number of molecules. We do this a lot in physics. And now you'll notice we're going to get an M, number of particles, over V, 1 over N. And let's see. So we're going to get M times N over V. It's going to be our average value of the velocity. So we could go through the whole derivation. We're not going to. We wouldn't do that until you were up to like a 400 level. But we know that this value is the same for X, Y, and Z. So we've been dealing with X. This is going to be the same for X, Y, and Z. And so then when a particle is moving arbitrarily, what we're going to try to find is the magnitude of its velocity. What did I do there? What's the superscript of 1/2? Square root. I don't like drawing square root symbols, so I just do it that way. You could do it with all of them. You could do cube root, raise it to the 1/3, fourth root, raise it to the 1/4. Same. I just don't like drawing the square root symbol because it usually looks pretty bad, because I try to do this and then and then it doesn't do right. So I don't like it. So we're going to square both sides. We're going to get the square of the total velocity, ux squared, uy squared, uz squared. And since we said x, y, and z are all identical, we are essentially going to get 3 Let's not skip a step. So 3 times that original velocity we were studying. We then know our average value. Will look like that. Man, did I not give myself enough space? I thought I gave myself plenty of space. So now we're just dealing with a generalized average velocity, which gets us now to our equation. If you put everything back together, because remember, this was pressure. We have P, V was number of particles times the mass of each particle, 1/3 average velocity squared. We're getting closer and closer to the ideal gas law. Crap, I'm out of room. Okay, hang on. No. I'm trying to move you there. Move you there. Trying to get you over here all the way. Okay, now we're going to start dealing with the fact that these molecules are moving. So what kind of energy do they have? Kinetic energy. Kinetic energy is 1/2 m v squared, which we've been dealing with. We also know in statistical mechanics that kinetic energy of a gas is 3/2 kBT. Kb is something called the Boltzmann constant. Oh, God, there was a physics book that actually started. I don't know if I should tell you. It's not exactly kosher anymore. Ludwig Boltzmann was a famous physicist. Since it was in a textbook at one point, some author had a really dark sense of humor. And he said, Ludwig Boltzmann studied statistical mechanics and the movement of gases for his entire life. And at the end of his life, he took his own life. His graduate student picked up his work. And at the end of his life, he also took his own life. And now, my dear students, it is our turn. It's, it was a different time. It was a different time. It was one of those. Oh, okay. So we're getting done now. Okay, so did I write down anything I put down here? No, not yet. Okay. So that means that we have 1/2 mass velocity squared equals 3/2 kBT. And if we solve for the average square velocity, we're going to get 3 kBT over the mass of each particle, which when we plug back in, we have PV equals 1/3. And we're going to plug in for U squared, 3 kBT over M. PV is now going to be in kBT. So we're a lot closer. Did I put it down here? Yeah. Okay. Yeah. So the little thing we're going to play on is number of molecules equals number of moles times Avogadro's number. So we're going to end up plugging that in there. And so when we plug that in, we're going to have PV equals number of moles, Avogadro's number, KB, T, NAKB is what we know as our gas constant, R. So kind of a little foray into statistical mechanics. This is, here's the thing. I told you this at the beginning of class. This is not something you would have to reproduce on an assignment or an exam. But I told you I'm not just going to make you go to the book and go memorize this equation. Everything we use comes from somewhere. We don't just do things arbitrarily. So yeah, this may be your first year at college, but I'm going to really try to push you outside your comfort zone and show you things you've never seen before. Because one of the biggest points, especially when you're looking at physics, is it's not just about memorizing an equation and plugging in numbers. You are trying to model the world around you mathematically. You're trying to, in every science, you're trying to model the world you're observing. Right now, you have textbooks you can reference. By the time you get to the point where you're called doctor, you have to do it from scratch. You just have to look at the world around you and devise a model. And that's where a lot of this stuff comes from. It's super nerds just sitting around for days on end going, oh, that's not right. And it's just over and over and over again until they find a model that is actually predicting what they're observing. Eventually what we do is we end up solving these and we end up with an equation. And this is why I use U, because they put this in the book, called the root mean square velocity. Because the reason it's called root mean square is you end up with the average value squared square root. That's why they call it the root mean squared. So this is essentially the velocity of a gas molecule anywhere in an environment. Let's see, M on the bottom, that is your molar mass of your gas. So that'd be your grams per mole. R, I want you to pay attention. You have a new R value. Remember I told you for your gas equation, you get to 0.08306. So this one, you're going to use 8.3145. What is that J? It's joules per Kelvin. Joules is a unit of what? Energy. So molecules are moving, they have kinetic energy. Eventually, when you want to get to velocity has what units? Meters per second. And we can only get that out of joules. Now, also, you're going to end up doing things where you're using R in calculations like enthalpy. You know, enthalpy is always in kilojoules per mole. So again, you would use this constant. And so you're going to get to a point where your joules, one of you said it earlier, the Newton. The joule is the Newton meter, Newton times meter. Or the joule is the kilogram meter squared per second squared. So you get meters per second out of this. Well, This will be the average velocity of a gas molecule moving in space. So again, your joule breaks down to the Newton meter, and the Newton is the kilogram meter per second squared times meters. Kilogram meters per second, meter squared per second squared. So you can see where we end up getting the velocity units out of this. So again, when you're picking constants, look at the units on them and try and make sure you're selecting appropriately. Yep, more space, but whatever. Okay, so another thing we want to think about is effusion versus diffusion. Effusion, So essentially you have gas on one side, you have a vacuum on the other side. You poke a little hole in the wall between the containers, the gas from one side flows into the other side. That's effusion. So gas flowing into a vacuum. And here you see we have, and this ends up coming from the root mean square velocity. Graham's law of effusion. You have the rate of gas 1 over the rate of gas 2. It's going to equal the square root of the molar mass of 2 over the square root of the molar mass of 1. And those rates are your root mean square velocities. So if you took that equation for root mean square velocity, you put 1 over 2, and you started canceling out and simplifying, you would end up with square root of m2 over square root of m1. Now, diffusion. Diffusion here is you see both sides have a gas, you open a hole in the middle, the gases mix. That's diffusion. You can actually use the same rate equation to figure out rate of diffusion. All right, now that I have you all thoroughly confused, let's solve a problem that you would be expected to solve. It took 4.5 minutes for 1 liter of helium to effuse through a porous barrier. How long will it take 1 liter of chlorine gas to effuse under identical conditions? So we're looking for some time, okay? Well, what's the rate of helium diffusion? 1 liter per 4.5 minutes. Make sense? What is the rate of effusion for chlorine gas? It's going to be the same, 1 liter per what? Some unknown time that we want to know. Okay? So, a molar mass of helium, that's going to be 4.003 grams per mole. Molar mass of chlorine is going to be 70.90 grams per mole. And then we are going to use, well, because I want T to be on top, I'm just going to go ahead and set it up that way. So I'm going to say, let's see, rate of helium over the rate of chlorine. That's going to give me, see, I don't like square root of the mass, molar mass of chlorine over square root of the molar mass of helium. So when you're using this equation, however you set up the left, you just flip the other side. So what we're going to do is we're going to say, well, this is going to be 1.0 liters for 4.5 minutes over 1.0 liters for time. I'm just going to go, I'll plug these in a minute. And I'm going to go through and I'm going to solve. So I'm going to bring this denominator up here, this denominator up here. I'm going to multiply, cross multiply. So then I'm going to get Molar mass of my helium square root. 1.0 divided by 4.5 is 0.222 liters per minute. And then on the other side, I'm going to have 1.0 liters molar mass of chlorine over time. And then I'm going to solve for time. It's going to give me 1.0 liters. Molar mass of chlorine. And then I plug in, so my time, 1 liter, 70.90 grams per mole. And then you do some fancy calculator work, you find out that chlorine effuses 1 liter every 18.96 minutes. So that one's just taking Graham's law of effusion and using it. So we won't work a problem on this next section, but I want you to understand the difference between what we've been doing and real gases. So we've been dealing with ideal gases. Now we're going to be dealing with van der Waals gases. So we're going to have to start making corrections. So the first correction that was found, and this was really found experimentally, is your volume ends up being corrected to your volume minus N, still your number of moles, and B is an empirical constant that's unique to the gas you're studying. Okay? Because the way different molecules move will vary. So you need some kind of constant to multiply by the number of moles that is going to regulate that. Because another thing that's happening is van der Waals forces are going on inside it. Gases aren't just moving. They're not just like balls moving, bumping into each other, going all over the place. Van der Waals forces are electrostatic forces between molecules. And so what you find is you have some molecules that are neutral. They undergo what's called instantaneous dipoles. Electrons shift inside the molecule. You can end up getting a positive region, a negative region on the molecule. That's going to affect another molecule. It's just going to be a chain reaction of dominance. And so you're going to start to get attractive and repulsive forces based off plus minus interaction or plus plus minus minus interaction. So these are going to be your van der Waals forces that are contributing to the motion of the gas, rather than the gas just floating around and bumping into things. So as you see here, we have from the ideal gas equation, number of moles over volume. We take that to N over V squared to account for interacting pairs of gas molecules. Now we have to start considering multiple molecules. And so we end up with another van der Waals correction where you're accounting for pairs of molecules interacting and then another constant A, a scaling constant, which again is unique to the gas that you're studying. So what we end up with is instead of the pressure in the ideal gas, we end up with an observed pressure. We have nRT over the volume fraction, and when you're subtracting off, this new correction factor of A multiplied by the N over V of molecule pairs. And you end up with the equation on the bottom, which is the van der Waals gas equation. I'm not going to put this on any assignments or exams. I just want you to know it exists, because every time I've ever seen this on a standardized exam, they always ask some kind of conceptual question. You just have to realize that gases very rarely, there's only certain circumstances where gases behave ideally. Otherwise, you're dealing with a van der Waals situation, and you have to take into account the corrections. So gases, they go okay. The kinetic theory of gases is kind of hit and miss for some people. What? But yeah, that I laughed at that one for like 10 minutes. So again, I wanted to end this chapter by saying, by showing you this. We're not going to do exercises. I'm not going to put it on assignments. I'd rather you learn how to solve ideal gas law first. I want you to know this exists, and that there are correction factors from ideal gas to real gas. Okay, so we're going to keep plowing along. We're moving up to chapter 9 now with a little bit of an introduction on something you didn't get in depth. So we're going to be talking about covalent bonding in orbitals, because I know you guys didn't get to orbital hybridization. But I'm going to try to throw in molecular geometry along the way. But I'd rather get through this and molecular orbital theory, because again, this stuff shows up randomly on standardized exams. It's hard to predict where. However, I think it's back in chapter 4. You were saying that you guys didn't really cover redox in depth. And you're really going to want to know how this works, especially, who's going on to microbiology next year? So you're going to want to understand redox cycle. Okay. So some standard definitions. We have oxidation. That's where an atom will lose electrons and become more positive. Reduction will be opposite. An atom gains electrons and becomes more negative. And then the oxidizing agent, reducing agent. If you figure out what's oxidized and what's reduced, you just flip them for the oxidizing agent and reducing agent. The oxidizing agent is the compound in the reaction that oxidizes the other atom. So it's the compound that contains the atom that's reduced. The reducing agent is the compound that reduces in the reaction. So it's the compound that contains the atom that's oxidized. And then, of course, we need to figure out oxidation number. We do that a little bit. Okay. Okay, some very basic oxidation number. So the way I do this is I actually give you lists of rules. And if you follow these lists of rules, you're going to do pretty well 99% of the time. You can kind of go down 1, 2, 3, 4. So like an oxidation number of a common elemental form is always 0. If you have a chemical equation that has solid iron, it's 0. If you have a chemical equation that has chlorine gas, so Cl2 gas, it's 0. So you're going to want to try and get down some of your standard elemental forms. The oxidation number of oxygen in almost every compound is going to be a -2. So it's always a good starting place. The oxidation of hydrogen in almost every compound will be a +1. Another good starting place. If you have hydrogens and oxygens, go for them first, have them help you figure out the others. Never start with carbon. Carbon's a weird one. Carbon could be 0, carbon could be 1/2. Carbon can be -7. It's bizarre. The oxidation number in fluorine in all compounds is a -1. You notice I said other halogens usually have an oxidation of -1, but they can vary, but you can use those as a starting point if you need to. What's that word halogen? Yeah, so 7A or 17. So depending on the periodic table you're looking at, So it's that last column of elements before you hit the noble gases. You're going to want to make sure you know names of certain groups of elements. Like, oh, everyone says this differently. I call it the calculants. You what? Yeah, so that's the oxygen group. If a compound does not contain oxygen or hydrogen, start with one of the atoms that you know has a common charge. You should know common charge ions from their position on the periodic table. Like your second group, all of those atoms will be a +2. Like calcium +2, magnesium +2, group 1. Those are common charges of +1, potassium +1, so on and so forth. Your nitrogen group would be, for the most part, a -3. Your sulfur group, then, so like, you think sulfur is right below oxygen? So that group is going to be a -2 group. You can start like that. Look for common charge ion. And for neutral molecules, whatever you put in as your initial oxidation numbers, you look at what's left, and you're going to, like for a neutral molecule, whatever you put in has take all of those charges and sum them to 0. If you have an ion, look at the chart, like if you have a -2 ion, well, whatever you put in has to end up adding to a -2. So an example of things that will be 0. So here we have some of your common elemental gases. I'll change it and put the correct size out. I always forget. It's a bromine or iodine. Anyway, I'll get that fixed. Those aren't all gases, but like your Br2, your I2, your N2, that's a gas, F2 the gas, Cl2 the O2, H2, metals. You see how the metals are represented as solids? Your noble gases, it's just going to be the element and the gas. Other compounds that are standard, phosphorus, so P4 solid. Your sulfur is S8 ring, solid silicone, solid silicone. So this one, C with the subscript graph, what does that mean? What are the 3 types of carbon? No, not isotope. What are the 3 structures of carbon? Diamond is one of them. Graphite. So graphite carbon is your common elemental form. The 3 forms: graphite, diamond, graphene. So all of these, if you solve them in a chemical equation, will have a 0 charge. And we'll move on from there next time, start working on some of these equations.